find it all alone, thinking that I'm with you, thinking I were to, but you're gone.
Hello everyone, this video are prepared for our lecturer Dr. 𝐿𝑒𝑒 and the group members are Siti Duratul Ain, Siti Nur Emiliana, Shafiana and Valeria Clarissa. In this video, we will present about applied maximum and minimum problems in the topic application of differentiation in Calculus 1. We will learn what is applied maximum and minimum, where we use, how to solve and discuss a problem and solution for the problem. So let's start with the introduction. What is applied maximum and minimum problem? The process of finding the maximum or minimum values is called optimization. A practical example might be minimizing the cost of producing an automobile given certain known constraints on the cost of each part and the time spent by each laborer, all of which may be independent. Regardless of the application, the key step in any maxima or minima problem is expressing the problem in mathematical terms,
where we use maximum and minimum problem. The problem of finding the maximum or minimum of function is encountered in geometry, mechanics, physics, and other fields, and was one of the motivating factors in the development of the calculus in the 17th century. Everything in this world is based on the concept of maxima and minima. Every time we always calculate the maximum and minimum of every data. Nowadays, results are also based on the concept of grades, which is again based on the concept of maxima and minima. How to solve maximum and minimum problems? This is the procedure for solving maximum and minimum problems. Step 1. Understand the problem. Ask yourself what is the unknown, what are the given quantities, and what are the given conditions. Step 2. Draw an appropriate figure and label the quantities relevant to the problems. Step 3. Find a formula for the quantity to be maximized or minimized and use the condition state in the problem to express the quantity as a function of one variable, which is y equal to fx. Step 4. Find x when dy over dx equal to 0, let x equal to c. Step 5. Find d2y by dx squared. Step 6. Insert x equal to c in y to get the maximum or minimum value for y.
So let's move on to discuss the example of applied maximum and minimum problem. The question are, we are going to fence a rectangular field. If we look at the field above, the cost of vertical side are $10 per foot, the cost of the bottom is $2 per foot, and the cost of the top is $7 per foot. If we have $700, determine the dimension of the field that will maximize the enclosed area.
Here is the solution for our problem. Step 1. We have to understand and draw the problem. We could probably skip the sketch in this case, but that is a really bad habit to get into. For many of these problems, a sketch is really convenient and it can be used to help us keep track of some of the important information in the problem and to define variables for the problem. Here is the sketch for this problem. Next, we have to write the equation. We are told that we have $700 to spend, and so the cost of the material will be constrained for this problem. The cost for the material is then 700 equal to 10y plus 2x plus 10y plus 7x equals to 20y plus 9y. We are being asked to maximize the area, so the equation is A equal to xy. Now, let's solve the constraint for y. That looks like it will only have one fraction in it, so it will be easier for us to solve. Y equal to 35 minus 9 over 20x. Plugging this into the area formula give AX equal X bracket 35 minus 9 over 20x bracket equals to 35x minus 9 over 20x squared. Finding that critical point for this shouldn't be too difficult at this point, so here is that work. A prime equals 35 minus 9 over 10x becomes 35 minus 9 over 10x equals 0, and our x is 350 over 9. The second derivative of the area function is a double prime x equals minus 9 over 10. From this, we can see that the second derivative is always negative, and so ax will always be concave down, and so the single critical point we got in step 4 must be relative maximum. And it also gives the value of a maximum's area. Last step is by getting the second dimension, y equal 35 minus 9 over 20 bracket 350 over 9 bracket equals to 35 over 2. Then the final dimensions are x equals to 350 over 9, meanwhile y equal to 35 over 2.
Conclusion: when doing this question, remember to draw and label following problems given and figure out either it minimize or maximize. Write the equation with the variable. Use first derivative and second derivative method in solving the problem. And lastly, make sure to retake step and your solution, and we are done.
Lying about her phone, thinking that I'm with you, thinking I were to, but you're gone.